Hi and welcome back. I am going to talk a little bit about the varieties of spanning tree protocols now. This is part 2 of the 3 in the spanning tree chapter. I've kept this one bare bones, so it shouldn't take too long to get an overview of what we're looking at. I'm hoping you get this before you read the chapter, but maybe it'll just be a good review because there are several different types, and trust me, even after you've read it a couple times, keeping them all straight can be a little bit confusing. Fortunately, we just use one at a time. So let's talk about the different types of spanning tree. When we talk about the list of spanning tree protocols, we have a couple instances of STP. We'll just have one listed here. And noticing that we first had spanning tree protocol, and then PVST, which was a Cisco enhancement of that, made things go a little bit quicker. Still, because the per VLAN spanning tree is what that means. And by per VLAN, it ran several instances of spanning tree at one time. Thus, you'll note that in the when it came to processes here, it goes from low to high process for a spanning tree versus per VLAN spanning tree. The more VLANs you had, every time you ran it, you had to multiply the amount that went in, amount of processing that it took. Then things evolved to rapid spanning tree, and that was an open system, and then Cisco enhanced that with Rapid Spanning Tree Plus, which allowed for very fast convergence, very, very high resource overhead though. And then now we have MSTP, Multiple Spanning Tree Protocol, which is a Cisco version that comes out. And we'll talk a bit about those. So when we look at PVST, we have PVST Plus, I should say. The plus is part of that. PVST Plus includes the root port for, see a root port here for VLAN 20. All right. And then we have a root port here for VLAN 10. Now notice that the trunks, instead of the spanning tree instance that we saw shut down earlier, where one of these ports would be blocking, with the per VLAN spanning tree, instead of turning down one of the redundant connections, we can just run certain VLANs over it. So VLAN 10 will run on the one over here, and VLAN 20 will run on over here, but it will block the other VLAN. So this has the same benefit of spanning tree, because in the VLANs, they're like local area networks. The loops won't update, the MAC addresses won't be shared between VLANs. So it will still be loop free, but it can also load balance. It won't be taking up near as many resources as in other sections. So optimum load balancing is really what this is about. And there's just one spanning tree for each VLAN maintained. So just remember that the per VLAN spanning tree means the spanning tree runs in software for each one of these. Okay? So let's move on. Now, port states. When we talk about port states in common spanning tree, CST, which is the regular name for spanning tree, there are the 5 port states we talked about: blocking, listening, learning, forwarding, and disabled. And this takes quite a bit of time to get through. About 40 seconds every time you boot up a switch, because the switch has to block traffic so that there isn't a loop, while it listens to receive any bridge protocol data units coming from other switches. And as it gathers those BPDUs and then floods them back out, as that happens, they learn all the MAC addresses in the table, figure out what will work, and once the BPDUs are received and calculated, then it figures out which ports can forward and which will disable. All right. So those are the port states. So if it's just, blocking, not disabled, because disabled just means it's shut down and not participating at all. All right. So the Now the extended system ID in PVST operation, when we talk about choosing a root bridge, this was the extended system ID took the 32768, which was the default in basic spanning tree, and added the VLAN ID. So the bridge ID is the basic 32768, which is the default ID, and adds, say, VLAN 2, the number 2. VLAN 1 would be 1, VLAN 20 would be 20, etc. With that ID added, then that could separate the VLANs by instance, and then each VLAN could have its own root port, root bridge, etc. The root switch that could manage the other traffic. So it's possible, as we saw in the diagram earlier, to have more than one root port per network, so long as you're working on other VLANs. Now, this next section is a look at rapid PVST. Again, this is a Cisco proprietary one. But rapid PVST changes the function of spanning tree just a little bit, but, well, not just a little bit, it's a pretty big jump, because it's designed to eliminate that huge 40-second wait time while the switches come up and run the normal spanning tree protocol. 40 seconds in computing time is eons and eons, and rapid per VLAN spanning tree can take that away and sometimes resolve it in just not even a whole second can bring it up. Now it still runs the independent instance of rapid spanning tree for each VLAN. All right, same deal. And it supports a new port type, the alternate port, in the discarding state, which is right here. We're looking at the alternate port down in F03, pardon me. So this alternate port discarding is, instead of blocking, it just holds the data and discards data until it fails over and it's time to keep processing. So it's active and going all the time, but it's just throwing away all the packets it receives instead of blocking them. And then if there's a failure or some need for it, it can roll right on. So there's no blocking ports in rapid PVST. All right, that's a huge deal. So the port states discarding, learning, or forwarding, that's possible. And then the alternate port DIS. All right. So RSTP supersedes the old STP, but it still works with the old as far as the BPDU formats and guards, etc. So the flag field, etc. uses all 8 bits. So it's a big difference going to rapid PVST+. So the RSTP bridge protocol data unit, the flag section here, you can see there's the learning, pardon me, the learning, forwarding states, all of these flags, the port role, unknown, alternate, backup, root port, designated port, all of these little numbers, we could actually find those in Wireshark if we went looking. All right, so that's the bridge protocol data unit. Remember, 2-second hello time. If it misses a few hello times, it would start recalculating. Now, edge ports. When we talk edge ports, it's because we're never going to have a switch attached to them. An edge port would be something like switch 2 here in this diagram. Switch 2 is an edge port because PCs 1, 2, and 3 are connected to it. If no switch is ever going to be attached, then there's no need for spanning tree to be working. In the previous versions of spanning tree, we would configure those. We would configure access ports or edge ports here with a spanning tree port fast command. And that port fast, instead of going through the spanning tree 40 seconds, you boot a switch and they come up right away. But you had to make sure that no switch would ever be attached, because if it were, then it would go down. All right. So here we are. Link types. Remember, we have a root port, a root bridge, as you know. Now, on the root bridge, there are no root ports because the whole bridge is root. So we have designated ports. Designated ports are ones that traffic will, by default, go out of. So designated ports are working. So we have the root bridge, and then a root port is the one that receives the connection to the root bridge on the switch. So think of a root port as connecting to a root bridge. The designated ports are ones that are designated to forward traffic. Now out here, to break up the loop, we have the alternate port discarding, and that means that switch 2, the traffic will get to switch 2, but it will throw it into the bit bucket and throw it away. And then the edge ports down here are defined because they go to computers. Nothing's going to be run on those. And then root port F connects to the root bridge. So that's a quick overview of the link types in rapid per VLAN spanning tree. So I hope this was helpful, and go ahead and enjoy the second section of Chapter 2.